Thank you everyone for coming for the second talk this week on Unix libraries. And just a little disclaimer, or not disclaimer, piece of info for you at the beginning. I have a lot of examples. I'm not necessarily going through an entire tutorial how to use MP units or other Unix libraries in detail, even though I show some examples. I'm more talking about how these can be extended for non-physical Unix use cases. But as I'm going through, if you're lost and don't understand something, please feel free to interrupt me to ask a question along the way, because there's a lot of material and we might go kind of up near the end, but hopefully I'll leave some time for questions. And but if you ask a question along the way, I also might ask you to save it for the end, depending on what the question is and what material is coming up. So I'm Roth Michaels, and oh, I thought I dragged some slides out of order, but it's okay. I'm principal software engineer at Native Instruments, a company that is an audio company. If some of you know me from Isotope, we're now part of a bigger family of audio companies working together. We make hardware and software, but primarily a lot of what I deal with are making plugins that run in other audio editors or video editing software. So you see here a few of our plugins on top of Logic, which is Apple's audio editor. And this will come up later because in this context, we don't control the whole world. So there's certain things about how some of our units might relate to each other that depend on the context of the host application we're running in. So this will come back later. And just a little thing I wanted to mention at the beginning before we get started is that if you're watching this live or on YouTube, I just wanted to kind of encourage everyone to think about presenting at conferences or sharing what information you have to share. I'm not some magical expert. I'm someone that just cared about this topic and wanted to learn more about it and share it with you today. And so if you have something that you have done that you think is interesting, or there's something you want to learn about, I encourage you all to give a talk. And this scary picture here is something that Midjourney came up for me. When I was thinking of this opening statement, I remembered the Rosie the Riveter, you can do it magnet my mom had in her fridge, but that's just a white lady, so I wanted something more inclusive. So I asked Midjourney for a Rosie the Riveter alien, and I'm sorry it's a bit scary, but I've never seen something not scary from Midjourney. Anyway, a little bit background about me quickly. I studied music composition and actually got into programming, making my own tools. I was using something similar to that Buchla modular synthesizer on the right, and then below that, a kind of virtual version of the same thing. And I thought to myself, why can't I turn these knobs more? They're just numbers, it's just math. Can't I just do it however I want? And we'll actually see later, numbers aren't just numbers. They also are measuring quantities and they have units, but just wanted to share that as something coming full circle. I spent a number of years as a polyglot consultant. I was a little bit involved with the Swift evolution in the early days of it being open source. But then I started working at Isotope and now Native Instruments, so I've been deep in C++ for 7 years working on digital audio. And along the way, have written some artisanal quantity and unit classes to deal with things within our libraries. So why do units matter? You might need them to make it to Mars. It's kind of the most classic unit example, and I borrowed some of these slides from Mateusz from a lightning talk he did, but we had the Mars Climate Orbiter that launched in the late 90s, and actually I heard there was also maybe supposed to play some music as a signal as well, but I couldn't look this up and prove it, but somebody told me this. It cost a lot of money, and it never made it to Mars. It was supposed to orbit like this, and it missed. And this came down to the fact that it was a mix-up of Newton seconds, and I think I had it in my notes somewhere. Oh yeah, here it is, pound-force seconds versus Newton seconds. They mismatched in the code because they were just floats, and the math was wrong, and they missed Mars. And it also matters in less expensive use cases. So I was working on this module in Ozone, our mastering software, when I first joined Isotope, and this was so expensive that you basically can't use it in debug build. So I made a small change, and the QA engineer next to me that had a fresh release build built, he built it, and then came over to me and said, "Hey, Roth, when I press this listen button, is it supposed to make any sound?" And it turns out it did after 30 seconds instead of 35 milliseconds, because I remember thinking, oh, I bet I did this math right, and no, I did it wrong. But it's not just not making sound, it's not life or death or millions of dollars, but bugs in audio software can damage people's hearing, it can damage their speakers, you can have a crash during a live performance, so we take it seriously even though we have fun and no one's gonna die. Just want to mention along the way, I actually did earlier, before some of the things I'll talk about this talk, looked at boost units, but I gave up because this documentation had all these macros and all these things you had to do, and I got scared and stuck with my artisanal stuff instead. So my journey to MP units, which is the library I'm going to be using as an example today. And I think 2019, there was a proposal from Timur Dumler, P1386, for a standard library audio proposal that was pretty big in scope. It didn't really make it very far. And for me, there's a lot of stuff in a 20-year code base. We weren't going to adopt a lot of the higher level things that were in this proposal. But what me and a few other people at Apple and other places in the audio industry talked about afterwards that we wanted was maybe there's some more useful vocabulary types we could have for dealing with audio, like buffers and multi-channel data. Turns out we actually got MD span was coming, and so that maybe solves this for us. We're still looking into if that's actually good for our use case. And also things like frequency, if we could use those as nicely as stood chrono, that could be nice as well. And so I was interested, okay, maybe the smaller version of standard audio is you just start with some vocabulary types and units. And so I was looking around to see what other prior art might be involved with this. And somewhere along the way, this is over years, I kept thinking about this puzzle in my mind. And I found this MP units library and this paper from Mateusz, a C++ approach to physical units, which surveyed a bunch of libraries. And I thought, oh, I kind of like how this one works. I think I'm going to kind of explore this, even though I might not be able to use it in production, and for my exploration of units. And this was all before the AU library that Chip presented the other day came out. But I think that also has a lot of interesting ideas. But I was not aware of that at the time. And so something I came up with a question talking to my colleagues is, well, wait, why are you looking at these libraries? Are physical unit libraries even for us? Like, we're not dealing with physical units. Well, the answer is yes. These libraries, even though they almost all have physical units in the title, they work with quantities of things you can measure and count. The examples from SI are about physical things, but they can be about anything you could count. You could have a unicorn, counting unicorns with Avogadro's number if you want to. I don't know why you would do that, but you could. So some of the things that come up for us in talking about using third-party libraries for physical units is like, they don't cover our use cases, as I said, about the physical nature. Do they handle nonlinear units? The N Holthaus library does have a technique for this, and there's open issues for MP units and AU about this. And then the other big question is, how do we deal with these plugin APIs and third-party libraries? They're handing us bags of floats to deal with, that we know what unit they are, and like, how do we interface with that, or the fast libraries from Intel and Apple for doing math. And so we'll look at some examples at the end of the talk about how I would approach third-party libraries. So just to give you a brief intro, Hello units, we're going to look at the Hello documentation from the MP units library. If you want to kind of know a lot more about this, Mateusz has a good talk from, was this ACCU? There's a QR code and YouTube link there for that. I promise I'm not a plant. He and I only met this summer at C++ on C after I'd already proposed this talk. And he told me, oh, guess what? You get to learn the new V2 version of the library for your talk, which is actually great and a lot nicer than the old version. And also, if you didn't see it yesterday, if you're interested in units, when it goes online, I would also check out Chip's talk about the AU library, where he also covers things to think about in a number of other units libraries. Just a few conventions, just know about the slides. Everything on here probably should be inline and const.expr. There might be a few places where I took off the const.expr inline to save room. It's all one translation unit, so we're not going to have ODR, but just keep that in mind. Anything in the MP units library has been used into the global namespace. So you'll see any unqualified names are from that library. Qualified names, you'll see standard library stuff. And then NI : is any of my examples. And TP : is an example of a third-party API we're wrapping, unless you see some class is defined in the global namespace on a slide. And oh, that was a scratch space slide I should have deleted, sorry. Okay, here we go, Hello units. So this is kind of not what I saw for the V1 when I first saw MP units, but if I was imagining today, I explore it for the first time, I look at the docs, I see this, I think, oh, this is pretty cool. If I want kilometers per hour, I can just type 110 times kilometers divided by hours, just like I would write by hand on a piece of paper, or 70 times miles per hour. And this is how you create units. And I'll be printing a few slides, comments below, like what that value would print if you printed it. And you'll notice I'm not using a constructor for creating something out of like a miles per hour, parentheses 70. I won't go into the details, but this is something that stood chrono allows you to do that this library does not, to avoid some weirdness with in place back and vectors, et cetera. But also I find it much nicer, instead of having MPH parentheses 70, this way it actually reads just like you would read any other, as you'd say it out loud, 70 miles per hour. Another example is, oh, let's imagine we want to calculate an average speed. And so we'll pass some things into it, like instead of just saying miles per hour, we're saying 20, and it's specifically a distance in kilometers times 2 hours, or a distance below that we're creating with miles. And what might this average speed function look like? Well, we can just make it completely generic like this, where we divide the first input by the second input, but we want to make it type safe, and so it has a speed. So we can type the arguments. And notice this quantity of, this is a concept that tells you this is some type that represents a quantity of length. Or the second argument is some type that's a quantity of time. And then, oh, yes?
I have a question. Do I have a back in the library or is it a typo for the meters per hour? The files.
Right there you can see M.H.
Oh, no, I have a typo. I wrote that. This is one of the few slides I wrote by hand instead of copy and pasting the printout, so it's my bug, not your bug, I'm quite sure. We can double check. I can compile it afterwards and double check. Thank you. And then to kind of finish up these completely type safe, instead of just returning a length over time, we can actually convert that specifically into a speed. And then here's just kind of a few more things you could do. If we have a value that was previously in kilometers per hour or miles per hour, I forget which V3 was, we can say, oh, we want this in meters per second. Or you can use a cast to do this, or you can just turn it back into an int. So that's just kind of high level what the library looks like. And now we'll kind of get into some of the details that I've been playing with in conversations I had with my coworkers about units. So earlier this year, we were working on some very specialized, non-flexible types for dealing with decibels. Someone posed this question, are units real? And we actually were kind of debating this for a little while. It turns out we were actually just talking about different things. But if you think about an equation like this, force equals mass times acceleration, at least my physicist coworker claims, yes, this is real. Force times mass acceleration is a real thing, but those aren't units. We don't know what that mass is or what that acceleration is measured in. These are quantities. And the units are the things that we invent for counting quantities. So there's a, I don't know where it is, but there's an object somewhere that is the kilogram, and that's what we use for counting masses. And so that's what you saw here in this slide when we're saying distance kilometers for V3 or the different syntax for V4. We're saying this is not just any old kilometers, but specifically kilometers representing a distance versus kilometers representing an altitude. And then from ISO, here's a definition of what a quantity is: a property of a phenomenon, body, or substance where the property has a magnitude that can be expressed as a number and a reference. So if you go back, if you remember looking at these slides, that's what this multiply is doing. You're taking a number and multiplying it by some reference. And this reference can be a measurement unit, and it goes on to say some other stuff. And so when we're thinking about quantities, there's a lot of quantities that are related to each other, and they're something called a quantity kind. So everything in this graph are all different kinds of length, and you can see they have relationships, like width and height are both kind of sub or derived quantities of length, and then width could either be a thickness or a diameter, but a diameter is not a height. They're unrelated. And you'll see, I'll show some other examples later, but when you deal with conversions and casting, you can implicitly go up the tree, you can explicitly go down the tree, but you have to cast if you're going kind of across branches, and you can't go to some other tree that doesn't exist. And I'll show you a few examples of that. So this example will kind of get at some of this and also show you kind of a cool feature / gotcha you might run into with the library. So we have this square prism class that's going to take a width that's going to represent a square base, and then a height for our prism. And you'll see I'm taking some quantity of width and height in meters. And it has a volume method to return the volume for you. So you'll see there's a few different ways we can create this square prism. We can just say 1 times meters, 1 times meters. Or we could say, I don't know why I have the width height example. Oh, it's meters and kilometers. So I can say, oh, we want 1 meter by 1 meter, or 1 kilometer by 1 kilometer, and all this works. But you might notice, how am I able to pass 1 meter into specifically a width? That's because 1 meter is not a length specifically, but is a kind of length, which means that it can be any of these things in this chart, and it implicitly converts that way. And this is nice for making it kind of easier for users. And basically, even though there's a type-safe interface, the user gets a choice of how type-safe they want to be. Obviously, you can't put seconds in here, but you can put in meters, or you could say specifically, no, I want to make sure I'm not screwing this up, and I'm going to put in height and width. Notice when I said, when you're going down the tree, you need a cast. So when I make P4, I have to cast the length to a width. I can't just pass a length. I can do something that's a kind of length, like a meter, but not an explicit length. And if you notice, if I try to cast 1 second into a width for P5, I'm going to use that color for doesn't compile. That's not going to work. You're not allowed to do that because we see there's no time anywhere in this tree. I just want to briefly mention something that a coworker I was talking with was kind of dreaming of being able to do with the units library. Is imagine we had some scale function to scale the dimensions of this. I want to scale the width and height. I don't want to mix up those arguments, but they're not meters. A scalar is meters over meters. And so really all that is counting ones or doubles. And so I know some people might like a strongly typed thing for this, but I think there's a lot of reasons for the units and quantities library that doesn't make sense. So you really normally would have to kind of make your own better interface, like 2 separate methods, some struct with name value initialization, or maybe some other strongly typed thing to say what you need. But I think in general, this desire to have something stronger for scalar types is probably not that useful. But we'll see another example, hopefully, at the end about there was a use case for thinking about that. So that's kind of a brief introduction. Now we're going to get into the digital audio portion of this talk. So a few bits of background of things that we might care about in digital audio is, and actually stepping back a moment, we've adopted, around the time that first example of the doesn't make any sound, we leaned heavily into stood chrono, and we're like, okay, we're not going to do any time math on our own without stood chrono, but we only had that for time and not any of our other units. But we want something that works like stood chrono for a number of reasons. One, we're mostly operating on floats unless the math really needs the precision of doubles, and we'll go to doubles just for that calculation. And so we don't want some library, which some units libraries do, where under the hood, everything's always going to be double. If we say float, we mean float. If we say unsigned, we mean unsigned. If we say int, we mean int. We don't want to unnecessarily convert between milliseconds or seconds when we don't need to, because now the behavior of our code is different than it was when we were just using floats. And we're interfacing a lot with third-party APIs that are giving us float star stars, et cetera, and how do we deal with that? Also, something to keep in mind, as far as ISO and the SI units are concerned, frequency and modulation rate, even though they are both 1/seconds, are different concepts. You have hertz and baud. In audio, when you're dealing with synthesizers, modulation is a common parameter. In the audio industry, we don't deal with baud. Modulation is hertz from our perspective. So for our first example, we're going to talk about musical tempo. So bear with me while I get out of the presentation to do a little demo. So what I'm going to show you is we have this audio processor we have that is designed to create a reverb, so essentially a sense of space or echo around the room. And so I'm going to play this drum sound, and you'll see that I'm going to use this. Let me make sure this is adjusted how I want. Yes. I don't know how well you can read it, but this knob that says 2.5, that means it's going to be a 2.5-second tail of reverberation that happens after you hear these drum sounds. And so I'll just play that for an example very briefly. So here's what 0.02 seconds sounds like. But sometimes people might not want to actually specify this in seconds, but might actually want to specify it in relation to the rhythm of the music. So it has another feature that I can engage where I press this little time mode. Now it's, I don't know how well you can read this, but it's doing things like fourths, halves, et cetera. So these are musical note durations that it's doing now. So if I do dotted quarter note, and play this, and then change the tempo of the song, you'll hear that as it gets slower, it will ring out much longer. And I'll make you just hear the reverberation, so that's even more obvious. I'm gonna slow things down. So you get that big, long echo, and as the tempo of the song increases, the echo is going to get shorter. So that's what we're going to be looking at in this next example, is how we can do this with the units library instead of doing all this math by hand for ourselves. And one other thing also take note, I don't know how well you can see it, but there's a little clock appearing up here, or maybe if I go over this view, you see this line moving across the screen. Most audio editors have a position in time, and they don't tell it to us in time, they tell it to us in pieces of a beat. And so that's the other example we're going to look at. And back to the slides. Sorry, just trying to get my mouse back to the screen. So as I said, the tempo, often in digital audio software, we're dealing with tempo in quarter notes, which are those notes kind of you see in the top of this row. And then we're dividing those into some subsection of that, sometimes 480, sometimes 960. I'm not going into details of this too much. If you're lost in this slide, don't worry about it. But to support this ability to set time in relative to a beat and a tempo, we need to define some new kinds of quantities and some new units. So the first quantity we're going to define is the beat count, which we're just counting the number of beats. So like in a lot of disco or most Western pop music, we have 4 beats happening at a time, and this has no dimension, and this is a kind of thing that is a beat count. The other kind of thing we have is a beat duration. So this is how much time every beat takes as you tap your foot to the music, and this kind of quantity is a derived quantity of time. And then we have tempo. That's what I was adjusting at the end, which is how many beats are happening over a unit of time. We normally talk about this in beats per minute. This is a frequency, and we define that as the beat count divided by time. And then to work with this, we're going to define some new units. A quarter note is our kind of base beat that we're counting. And then a number of other note durations we can define as, based on that, like a whole note is 4 quarter notes. I'm not going to go through all of these, but one thing to note, if you want to do half a quarter note, this is the syntax is this mag ratio 1-2 or 1-3 for the triplet. And then we can define a bunch of kind of shorthand unit symbols. So when I had the short, times m or times km for kilometers, here's my made up short names for the note durations. Naming is hard, don't worry about this. This is probably not the way I would do it in production. And just note, most of these are just short names for one of the units described here, but I can give a short name to something I haven't described. Like I never described a dotted whole note, but I can just do that in line here as saying, oh, that's 3 half notes. And just one more point on conventions. Since I'm not name qualifying it, if I've brought any of my own shorthand symbols in the namespace, they'll be purple in the slides. So what does this look like? So we might have some functions in our code base or provided by the third-party hosts we're running for getting the tempo, getting pulses per quarter note, so that's how many, our kind of smallest grain of time the host is giving us, and then a transport position specified in those pulses per quarter, and you see it's untyped, float, unsigned, or and unsigned. So we'll wrap them up in something nicer interface so the client code can actually get nice things out. So get tempo, we'll call our untyped one and multiply it, but we know this is a beats per minute. We know that get PPQN is a MIDI pulse per quarter, and the transport position is a number of MIDI pulses. And so when we do get tempo, you'll see it'll return 1 BPM. If we decide we have 1 NQD, which is a dotted quarter note, it will say 1 Q dot. If we want to turn that into a time, and that's what that time for that reverb tail was, we take the reverb beats, divide it by our tempo, and we get seconds. Actually, that probably should be wrapped in parentheses and say in seconds, I believe. And then for locating the transport clock, we get the pulses per quarter. I cast this to float because you see down below I'm dividing and I want this to be a floating point division. And I just put the cast there for slide reasons. We get the transport position, which is 15,836 pulses. If we divide that transport position by pulse per quarter and convert that to quarter notes, we get that this is a 16 and about a half quarter notes long reverb tail. And if we want to turn that into time, we take those quarter notes, divide that by our tempo, our beats or quarter notes per minute, and then convert that to seconds, and we get that it's about a 9-second long reverb tail. So the other kind of units that we're often dealing with in digital audio is digital sampling. So this is the time and values of all, whether it's on your CD, some of your streaming, this is what your audio is. And so we'll give you a very brief primer into digital signal processing. So if you have some analog signal like that's coming into a microphone and is being recorded for this camera, there's a number of, very quickly, we're making very small measurements of what that continuous audio signal is. And that is our digital samples. And that's happening at some sampling rate. For a CD, for example, that'd be 44,100 times a second. And so you'll see there's kind of two pieces of information we have is these samples that on their own, we don't know without the sampling rate how they relate to time. And so that's that T there, the time between measurements. And then there's also the value of these sample values, the kind of green dots on there. Basically, what did we measure at every point along this continuum? And this is actually what started the our unit's real discussion, because I was discussing what do we call that unit that we measure the digital sampling value at? And none of my colleagues, the more DSP experts, did not know the name for that. We looked around some DSP books. I don't think really anyone ever names this. It's just a digital sample that is a number, and you know what domain you're working with. The closest thing to a name I can come up with is, in some ways, looking at DSP theory, this all these different measurements you see. Another way to look at that is it's a scaled and time-shifted copy of what's called the unit sample. And the unit sample is something that has the value at one at time 0. And then any other digital signal is really essentially delaying that 1 to some other point in time and multiplying it by some other number. So the best I can come up with, and again, names are hard, we'll probably bike check for days before anything like this goes in our code base. But I figure this is the amount of unit sample you have. So we'll look at a few different examples, how we'd actually define both the time units and the amplitude, or actually magnitude, because we're caring about both directions of this digitally sampled signal. So to deal with time, as I said, this is similar to the beat count. We're going to count these arbitrary units of ones called samples. So we have a count of samples that we have. So like I said, a CD, you'll count 44,100 of those every second. We have a sample duration. Again, this is all just like the beats. We have a sample duration, which represents time. And we have a sampling rate, which is the frequency sample count over time. And usually we actually express that in DSP not as a samples over seconds, but as hertz. So again, like modulation rate, anything that is over time in the digital audio world, we usually just round that all to hertz, even though ISO might not think of it that way. And then we create one unit for this, sample, we call it in the C++ code, or when we name it in printing, we'll say SMPL, which is just the number. We're actually measuring the number of samples that we've counted. And then we have a shorthand unit symbol for that as well, SMPL. So the way we would use something like this to actually figure out how much time some arbitrary number of samples represents is, again, we're going to have to rely on some third-party API. We're going to need to ask our host environment, what's the sampling rate? And they give us that back in floats that, according to the documentation, we know are always in hertz. So again, we'll make that a little bit better API by saying, okay, we're going to wrap get sampling rate with a new function that we'll call the third-party one, multiply it by hertz. So now all of our client code is going to be able to use the sampling rate in hertz. And then here's what it looks like to use this. So imagine, I have two examples here. One, we're going to have sample rate 1, and we're going to use this for some conversions. So this is, imagine we've got some runtime value from the host. And then I've also actually just hard-coded a compile time value as well. Sometimes when you're prototyping, you might do that. And also to show you how samples over seconds and hertz are actually equivalent, because get sample rate returns a hertz. But you see here for SR2, I've divided 48,000, which is the DVD, and I think streaming video sampling rate, times samples per second. And then we have this next variable, samples, that we described, that is 512 times samples. And we can imagine this being some unit of work that we're processing in our audio process callback. And those are usually some power of 2 unit. 512 is a pretty common number. If someone's like mixing an album, they might be processing stuff at 512. So they don't need super low latency, but they get nice feedback from their control surfaces or whatever. And okay, we want to know in our current environment, what does 512 samples mean? How much time is that? So we can compute this very easily. We have a samples and a samples per second. So if we divide the samples by the samples per second, the samples cancel out, and we get seconds. And you see, if we want to express the 512 with our sampling rate of 44,100 in seconds, that's 0.01161 seconds. Our second, or if we say, oh, actually, this 512 is being interpreted with sample rate 2, 48,000, and we express that in milliseconds, we get 10.66. And if we want to know, well, wait, how long is just one of these samples? We can take the 1 over the sampling rate will give us a duration in time. And it will, if we put that in milliseconds, we'll see that's the duration. The duration 1 is how much one sample is at 44,100 times a second sampling rate. And the second value is what a sample duration would be for a 48 kilohertz sampling rate. And so that was how we're dealing with time. And then we can make some similar units for dealing with amount, although we don't need the rates. So as I said, digital samples are essentially how much of a 1 you have, because we're normally dealing with floating point values where 0.1 is the maximum value that your audio analog to digital converter or your digital to analog converter, basically your microphone or your headphone jack, the highest value it can handle. When we're dealing with floating point values in DSP, that's going to be 1. And so we're basically counting how much 1 do we have. And we can give this a few other names. This user sample amount I also can call amplitude and level. Although I've made a comment there, really an amplitude or level is something that should be non-negative. And so we'll get back to that a little bit later, but don't worry about that for now. And we can also describe a power, and that's a sample power is the level times the level. And we want a unit for dealing with this. Again, like I said, I couldn't find any book about what to call this unit. So in this slide, I call it sample value in the C++, PCM for when we're printing it for pulse code modulation. That's what the kind of sample encoding that we're talking about for CDs, et cetera. It's probably a bad name because you could have integers instead of floats representing your samples, and it's still PCM. So really that's PCM float 32 would be the correct industry standard thing. But PCM and PCM squared look nice on slides, so we'll call it this for slides, and when I get back to Boston, we can bike shed on this later. Just a little joke there. When asking about this and not finding any units, one of my coworkers suggested calling them ethiers, just naming them after the founder of our company, Isotope, or co-founder Mark Ethier, and it's a fun name to say, but I thought I'd confuse all of you if I did that, so we're calling them PCMs for today. And then, so you'll see that I'm using it, this is just my whole set of like shortcut symbols there. So we see we have our SMPL before, which is our sample count unit, and then PCM is our sample value unit. So those are the two shorthand units we'll use for dealing with digital audio. So as I mentioned, non-negative level and power is something we care about, and also decibels is something we care about. So go back to the audio demo again. This time, I'll mute the audio while I talk. We don't need to listen to any drums, but we'll just look at some meters for this example. So let's mute this audio. Oh, did that not save? Oh, I'm sorry. Well, we'll pull up the meters again.
Can you convert these meters to millimeters?
Nope, they're just meters. Different quantity kind. And, oh, no, they're here, sorry. I was just, live demos, you forget how to use computers. Okay, so there's a few different meters we're looking at here. So first we'll look at the left top meter. So this is kind of an oscilloscope showing you the drum beat that we're listening to, and you'll see that that is a bipolar value, so it's ranging from -1 to 1. This is our amount of unit sample unit that we're showing in that meter. And down below, you'll see a rectified waveform where it's the same information scrolling by, but you'll see it's just going in this case, we're actually showing in decibels. We'll get to that in a minute, but essentially 0 to 1, where that orange line is 1. And this is an amplitude, or in audio, we're often calling this level, which is a positive value versus the actual value of the signal. And on the right, we have a bunch of different decibel meters. So you'll see that we have on the bottom the level in peak and a RMS, root mean squared, don't really worry about that, which is one way of measuring decibels. And we call this in digital audio dBFS, essentially decibels full scale. So considering that you have a range that your sound card can make, these are decibels representing that full scale of the range. And you'll see that, the values are things like -3 and -14. But these other decibel meters up top, they're saying things like -17. And so those are not dBFS, but those are decibels loudness units full scale. And a loudness unit is a measurement essentially trying to measure not what is the value of the signal, but as a human, how loud do you perceive it? And so, because our ears hear the frequencies of the human voice a lot better than low frequencies, because when we're running from saber-toothed tigers and our friend is screaming, like, we've got to hear about that. So a lot of our hearing is about survival as early humans. And so anyway, there's some curves you apply and some other math to get an approximation. It's not actually 100% real, but it can show you how loud something is. And so we'll get back to this later, is that these are all decibel measurements, but the decibels on the bottom are not compatible with ones at the top, because these are different units. So 2 things to keep in mind. Level and power is something we're dealing with that's always positive. Well, power specifically because it's a square. And then there's many kinds of decibels. And we'll go back to the slides to do some math on that stuff. Oh, sorry. Okay, so don't worry that you can't read this. This is a helper class in the MP Units library for making instead of using like floats or ints as your representation type for the unit, you can represent some representation type that has some preconditions for how it's allowed to be constructed. It's not in the main library, but if you look in the examples, you can find this, and you'll see in the next slide, that's how I made my non-negative unit type, is copying that out of the examples. And not really get into all the details, but this is kind of how this works, is we make this, and you'll see it here on the third grouping, this validated type. So if you want to look this up in the library, it's called validated type. I really should have had a link, I'm now realizing, but it's MP Units. Catchy name, you won't forget it. And yeah, so this is basically how we set up. The first few lines are just setting up this ability to have a non-negative floating point type. And then on the bottom there, you see this sample power quantity. And so this is a quantity that is a power. So if you remember, if we go back, I think it was over here, sorry. Yeah, I described this power quantity here as being the square of levels, so that's what we're using here. So we're making a using template to say we have a quantity of power, and we're measuring that as the square of a sample value, or the amount of unit sample we have. And the type is some non-negative sample type, and we've constrained that on floating points. So it's either going to be a non-negative double or a non-negative float. And we can use it like this. So I've just kept that new sample power quantity type up there for you. So if you notice on the first line, when we compute sample value, we times negative 0.4 times sample value. So we have in that oscilloscope, we have basically almost halfway down the bottom half of the oscilloscope. And then we square that to make a power. And so that's going to be a positive number, 0.16. And so we can totally construct a non-negative sample power quantity from that. But if you look at power 2, where I try to construct one by hand, saying, okay, I want to make a sample power quantity of minus 0.2 times sample value squared, that's not going to actually this compiles, so actually I should use a different color. That's going to crash in this use case because I'm compiling with contract checking on and terminate on contract violation. So this violates the contract of sample power quantity, and so this won't compile. And I went back and forth on this, trying with coworkers, whether like this is something that should be encoded in the type, or should the APIs that use it just do the non-negative checking. I was, for a while, in the camp of the latter. I normally, when remembering C++, if I can, prefer very simple structs and maybe that don't really need an invariant. But if there's specific functions that expect something, I assert preconditions on those functions. The more I was reading about the ISO 80,000 system of units and the fact that there are quantities that aren't ever negative, I've come around, and actually playing with making these examples, I think I'm now in the camp that the quantity and unit types themselves never being allowed to be negative is probably the right way to approach this. It would be nice, though, to be able to not have to do this at the units level and be able to actually specify the quantity is always going to be non-negative, no matter, and not need to make your own representation type this kind of close to the user would be nice. I don't think we have this ability yet, but something we'll continue to discuss and work on. Because I think this library is heavily based on the ISO standard, and the ISO standard says that there are certain quantities that are non-negative, so we need to be able to specify that at the quantity level if we want this library to model the standard. So the next thing, remember, so now we're going to think about the meter on the right, we're going to think about decibels, and now we're going to uncharted territory. I'm not going to show you real examples that work with the library, but maybe more imagination examples that might show you how complicated it is to think about working with decibels. So the ISO 80,000, which is the ISO standard on quantities and units that the MP units library bases all of its built-in quantities and unit systems around, in addition to maybe supporting some other unit systems that are not part of this, it does mention some decibel-related values, like sound pressure level. When we're measuring sound pressure level is when I'm speaking to you, my voice is vibrating the air by making a kind of wave of high and low pressure that happens at you, and we measure that in sound pressure level in decibels. What you experience is the intensity of the sound, and that is a power of the pressure, and that's a power decibels versus a root power decibels. And so, so there's already some guidance about this in the ISO 80,000 about how to think about decibels. And I also want to point out that decibels are more complicated than just logs. So and we'll see some examples in the slides, but for example, log is also important and nonlinear for calculating pH. It's the count of some kind of ion. I'm not a chemist, I forget, I should have written it down, but you count some stuff in your stuff you're measuring pH, and I think you take the negative log of that or something, and that's the pH value. But that's really simple, because that's just a log of a value. And there's two kinds of log quantities or units that ISO talks about. There's logs of a value, and then logs of a value compared to some other reference. And that's the second category, is what we're normally dealing with in audio. But I feel that if we handle the basic case simply, like of log, if we can somehow do that in this library, like we do with power, that will cover many use cases. And then if we solve this decibel case, that will also cover basically everything ISO 80,000 supports. And so we would kind of have an ISO compliant quantities and units library if this library got those features. But maybe there's other nonlinear relationships you want to make that are not log related. Maybe it's some piecewise function you have or something else crazy. I'm not sure it's necessarily useful to have a complete customization extension point for any nonlinear relationship in a units library. But perhaps if we support log and decibels, we can cover most use cases. And I think stranger things, I'll cover one at the end of the talk, that users might want to do. I don't think we need to have a built-in facility to convert those in a units library, but perhaps it's more up to the user to write their own free functions to do their kind of wackier things that are outside of kind of more standard like log-based units. So this is something that might be kind of like code if it actually worked, but it doesn't work the way I want it to at the moment. And I certainly didn't try compiling this, but the math is good. So we're going to talk about not digital audio units at first. The bottom two are the dBFS I was showing you in that meter before. But first, we're actually going to talk about decibels for audio in the analog realm. So the wire that's coming out of my microphone right now is taking the sound pressure level through the transducer in the microphone and converting that into a voltage. And that voltage is then what we then later measure when we're digitally sampling to convert it into the digital domain. And there's two common ways that voltage are measured. And I forget off the top of my head which one is normally for pro and which one's normally for consumer hardware, but there's dBu and dBV. And they're both decibels measuring volts, but they have a different reference. And the dBu used to actually be dB lowercase v, but that was too confusing. So we have dBu is voltage with a reference of 0.775, and dBV is voltage with a reference of 1. And so we'll see how we have two reference constants above. So I've created U0 by multiplying 0.775 by V. I'm not sure if capital or lowercase v is how it shows up in NP Units library, but when I'm writing by hand, I write a capital V, so here's what I have here. And then our reference voltage for dBV, V0, is 1 times volts. So you'll see we can come up with, and then I have two voltage measurements below. I have a V1, 0.9 times volts, and a V2, 1.2 times volts. And we'll see that if we, I guess I decided not to use those. I was about to change my mind about this slide. We're just using 1 volts number. So pretend any V, it could be either one of these. Doesn't matter, because we're not actually looking at the actual values. I guess I decided to cut out all the printing of the values in this slide and didn't get rid of those constants. Sorry about that. So to calculate dBu, the calculation is 20 times a log in base 10 of your measurement in volts over your reference. In this case for dBu, 0.775. And if you think back to the earlier example of scaling the box, where I divided meters by meters and I get 1, you would expect here, if I'm dividing volts by volts, I also now have a unitless quantity. But even though you're doing that division in the decibels, when you're actually thinking about decibels, you don't lose the units. You know it's actually not that you did a division, even though division is actually how you do the math in the decibel calculation. It's actually much more like you're measuring a quantity point. So thinking in this terms of stood chrono, you have a stood chrono duration, which is a count of time, and then you have a stood chrono time point that is a amount of time since some other point in time, I think by default the Unix epoch. So a decibel value, and this is where it becomes different than a traditional log like pH, is more like a quantity point, where it's a measurement compared to some reference. And so actually the units still matter. And so you see below when I create, I create one pair of dBu values, one pair of dBV values. And then you notice with the dBu, if I subtract a dBu by a dBu, I get something in decibels in my example. And the reason for this is that we'll see that if we then for dB, I'll skip the purple stuff for now. If you look below it where I create dBv3, I'm adding a decibel in dBv. I'm adding to that the difference of two dBu values. And that actually is something that, as long as we're saying in volts, that totally makes sense, because the references change, but it's just like, if I measure 100 years since the Unix epoch, I'm allowed to add 100 years to today. That works totally fine. So when you subtract two decibel values with a reference, you get a referenceless decibel value. But it doesn't actually make sense to add two decibel values with a reference, just like you don't add two stood chrono time points. So that's why this dBx below is in purple, because that should not be an allowed procedure. Same thing, adding a volt and a dBu won't be allowed, and actually that probably should be an example of saying subtracting a dBV and a dBu also isn't allowed, because they have two other references, and if you do that, what's your, you could maybe say, oh, well, I can find my least common denominator reference, and I kind of was working out some stuff on paper about that, but I don't think that really makes sense, and you should never subtract 2 decibels of different units, unless it's this unitless dB that we get from subtracting 2 decibels. So you have a decibel quantity and a decibel quantity point that has a unit attached to it. Then the open question is, we also have, as I mentioned before, dB full scale. So we're no longer dealing with volts, but similar calculation. I have 20 times 10 log 10 of, let's say, 0.8 PCM, so that's our amount of unit sample, And then divided by the reference. 1 is how we get dBFS, as uses 1 PCM as the reference. Should I be allowed to add the difference of 2 decibel volts to a dBFS? Probably, because it's still just a relative measurement, but you're talking about a relative measurement between 2 points in the physical world that we deal with volts, and then add that to a point inside the computer. Maybe that shouldn't be allowed. I think that's an open question, and I need to ponder this and consult some other colleagues on this. But clearly the example of adding a decibel point to the difference of 2 decibel points with a different reference, that makes sense because we're still all dealing with volts. But when we look at relative decibels to a decibel point with different units, should you add those, or do we need to keep track of the unit even when you subtract them? It's an open question. I think it's one of the things to play with and discover. The other kind of mysterious question with decibels is there's 2 kinds of decibels. There's decibels when you're calculating them with a power or a root power value. So in the previous examples, we're dealing with root power, and you notice I have dBSF root power I make here, like I did before, with a level divided by a reference level. And then I have I'm sorry. Hey, I checked this for typos beforehand, but now that I'm doing it live, I'm seeing them all. That second one should just say dBFS power, not root power, I'm sorry. And that's calculated by 10 times a power over a power reference. And you notice I had this up at top, I declare this set level method that takes a quantity in PCM, or unit sample amount. So clearly, if I go to from unit samples to decibels of unit samples, I should be able to go back again to the same level, and that conversion should work. But if I want to be able to go from power level decibels into a PCM non-power but root power level, should that conversion work? Ideally, I think I'm talking with some colleagues, they'd like that to work at the call site. But to do that, not only does a decibel value need to keep track of what its reference is, it might also need to keep track of was it created as a root power or a power decibel. I'm not sure if we need to support that or not, but these open questions that I'm puzzling through. And just to briefly show you, I'm going to kind of move on to save some time. But this is an example of what like a dBFS class that we were using internally. It only supports 1 reference value. And you notice we've constrained the operators to only the kind of plus. This decibel gain is this the unitless dB I was talking about that is created by subtracting 2 decibels, or you can use that to add or subtract like I showed in the example before. And you'll notice there's no multiplies on here. Sure, if we used MP units to do this, we could do a decibel squared, and that would be fine. We did not do that yet because we didn't know the meaning of that, but I think it would be totally fine to allow users to do other operations on these things, as long as we can kind of separate which operations are allowed on a quantity point and which ones are allowed on the quantity. So we have the decibels with reference and the referenceless decibels. I'll skip these other examples of handmade unit stuff. But yeah, to kind of in conclusion on that, I think that we got to get log right and decibels, and I think we can leave other nonlinear relationships to the users. Like for example, to go from a waveform like we saw before to analyze the frequency content of that drum sound, we perform what's called a fast Fourier transform. And that actually does have some units attached to it. It would be like sample values times time, and then if you normalize for time, it's also like a power density per hertz. But I don't think we need to have facilities in Units library to support carrying units through an FFT calculation. I think we can write functions as clients that do the right thing for us in that case. I'm just going to super fast show some examples of how to interact with a third-party library and try to leave some time for questions. So often when implementing a plugin to run in some audio editor, you might have some virtual interface like this you need to implement. But it won't actually be like this. It won't just be a span of floats. It would actually be 2-dimensional because you have multi-channel audio. And sadly, it's not a span. It's a float star star and a number. But we have modern C++, so for slides, we'll make it a little bit less ugly like we're making a new plugin API today. But we don't want to just deal with floats. We actually want in our client code, when you implement this, to be able to deal with amount of unit samples, because that's what those floats mean. So here's an example of how this could look. I'm not going to go through all the details, but essentially I'm making a type def for a quantity of unit sample amount measured in PCM. That's a float that I'm going to use other places. I have a concept for my client code should have a process function that takes a span of these unit sample amounts. And then I have this implementation of a third-party processor called processor impl that is going to take its span of floats and reinterpret cast them to the structural type that is a float that is our unit type. And so now client code, don't pay attention to this silly printer class, exactly what it does, and don't ask me why I'm not using std format there, but that's a thing. But you'll see in the main down below, I create a processor out of this level printer, and so now my client code above, I didn't deal with raw floats, but deal with the units, and you see when I print this out, it prints these floats I put in as PCM because they're PCM in the client code. I'm going to go through this one super fast. You might want to check out the slides later because it gets a bit deep. But another one we run into are functions provided by the platform. So like IPP on Intel or the Accelerate library for Apple. There's these functions for doing kind of vectorized math that are the ugly interface like this. But we can make them a bit nicer by taking spans of quantities and scalar quantity and then calling into the third-party version of that. Here's what multiply looks like. I'm going to move that through fast. And so this is what, with the unsafe version, here's what developers would write. And so we have to get something almost as good as this to get our DSP engineers to want to use types in their code when they are used to just multiplying or adding and doing all this stuff on the same buffer. So this is what our templates I showed you before looks like. And hey, this looks pretty nice. We have type safe values. We see what we're printing at the bottom. Difference is we have to, instead of just operating on the same input buffer, because the types are changing, we get the output span and we put it in the next thing and get an output span, put the next thing. That's fine. I think we can sell that. The downside, threading through the outputs. The downside is I had to be explicit about these template parameters because they're not types, they're non-type template parameters, and those cannot be deduced in this context. But after chatting with Matyush last night, it is actually possible to use some tricky concepts to constrain all this. I'll let you look at the slides later to look at how this works, but instead of taking a span of quantities, we take a T that we constrain to something that is a span of these quantities, and then we have another less constrained one that takes arrays in and creates spans. I'll encourage you to look at the slides later because it's some cool concept stuff, but concepts are not the point of this talk. And then you'll see this is what it looks like with the new concepts. And so we don't have to put any template arguments, which is nice. We do have to thread the outputs, but I think this is something we could sell to our DSP engineers. Maybe I know one that is so good at math in his head he wouldn't like it, but most of us that want units I think would like this. And this is probably a good enough way to wrap those platform nasty floatstar APIs. So what's next for me and units? One of my colleagues the other day told me that the MP units library, at least the hello units example, compiles with the Xcode 15 beta. So doing IO development, we're normally held back by Apple Clang, but actually maybe not so much in this case, which is great. Also, might look at playing around with AU in the meantime, because we're not going to move to Xcode 15 this year, so maybe we can use that since it supports C++ 14. Working with Matyush and the other people working on MP units and standardization on how decibel should work. Some experiments with FFTs and units and units with complex numbers. And I have not written them, but sorry for tapping the mic. But I want to highlight these papers that are coming out to the standards committee soon regarding a standards proposal based on the MP units library. And just one note that I did not show in the slides. Don't worry about this if you're looking online later, but if you're looking today at MP units after this, when I showed you how to make a quantity, that might not work if you can't do the deducing this. So there's a macro. Just look in the headers, you'll find the macro, but we're not putting it in the slides. And thanks to some of my colleagues that had lots of nerd outs on units with me, and to Matyush for answering some of my questions as I was putting some examples together. And thank you to all of you for listening. And we have a few seconds left, so thank you. And what are your questions? Unix expert for first question.
Thanks for the awesome talk. It was really exciting to see in practice. I noticed in the last slides we had a lot of like reinterpret cast of like float star star, and there's some code that wants to see it as raw. Excuse me, out of breath. Raw numeric types, and some code that would like to see it as units. Whenever I see reinterpret cast, I'm always like not sure if it's like undefined behavior. So do you know if that's okay or if that's like a strict aliasing violation?
In NP units today, it's okay because it is a it is a structural type, but it's also that's not the thing that requires. It's that it's a standard layout type as well, and you can reinterpret cast a standard layout type between itself and its first member, and so that's how that works. And I did double check that because I was first trying to do something crazy with like start lifetime as,
okay,
but that didn't work in the compiler I was using, and then I realized, oh wait. Now that I'm looking at how the library is implemented, I didn't need that. Hopefully it stays this way that we can continue doing this.
Thanks.
Hi, thank you for the talk. I wanted to know if during your experiments you looked at the impact on compilation times.
I do not measure it. Compiling short files, it feels slightly longer than I would expect, but to me, I don't think that's not a concern for me for two reasons. One, I am responsible for some of the biggest template compile times in our UI libraries, and none of my coworkers hate me for it, even though we all know about it. I dreamed in 2018 that modules would save me. It did not yet. The other reason is this is using a lot of new features from C++ 20 and potentially 23, and so hopefully they're so new that the compilers will optimize them better over time. And in my experience in large projects, even for incremental work, whether it's incremental work or full clean builds, link time is actually the big bottleneck. So I'll take templates for some magic because I'm going to have to link forever anyway.
Thank you.
And you're going to get modules like 2 weeks from now.
Yeah, exactly. Yeah. Thank you very much.
Thank you.